Okay, it is time for us to propose a model or theory to explain how chemical reactions happen so we can reconcile this model with the data that we've obtained from our study of chemical reaction rates. This is called collision theory. It is based on the kinetic molecular model that you perhaps studied in Chem 1A when you studied the properties of gases. So we're going to assume that the molecules or particles of the reactants are moving about with a certain amount of kinetic energy. Collision theory proposes that in order for a reaction to happen, particles have to collide. This is going to cause bonds in the reactants to break and then new bonds to be formed, as we see in the following animation, where you see the green spheres approaching the complex molecule on the right, colliding with it and carrying away a portion of it to form the new products. Now, what is important in collision theory is that in order for the reaction to actually happen, the collisions must be effective. Number one, particles must collide with sufficient energy. And secondly, particles must collide in the proper orientation. Once more, let me take you back to some things that hopefully you remember. This is what's called a Maxwell or Maxwell-Boltzmann distribution. James Maxwell was a 19th century scientist who worked in kinetics, thermodynamics, and electromagnetism. Definitely one of the greatest theoretical scientists ever. Now, you may or may not recall this type of graph where you are essentially studying the average molecular speeds of molecules at different temperatures. Now, this particular diagram here is for nitrogen gas, and you're plotting the number of molecules versus the molecular speed. So what you get is a bell-shaped curve that is narrower or more spread out according to the temperature. Now remember that related to the motion of the particles and their speed, particles have an average kinetic energy. Here's the equation for it, where Ke bar is the average kinetic energy, and it is equal to 1/2 times the mass times what is called the mean square speed, which is not actually the square of the average speed. It's more of a statistical function that is drawn from this bell-shaped curve, right? Now, what we see here is that if you look at the peak of each one of those bell-shaped distributions, you can see that the peak of each curve is, at a higher molecular speed according to the temperature. So for 100K, the peak is somewhere in the 200 to 250, perhaps, meters per second range. At 300 Kelvin, it is probably around 400. At 700 Kelvin, it is roughly about maybe 600 or 700 meters per second. Now, let's say that in order for a process to occur, the particles must collide with a certain amount of energy. Of course, that means that they have also a particular, average or statistically mean molecular speed. Let's say that we need for the particles to be traveling roughly at about speeds greater than where this bar is at 1,000 meters per second. You notice that at 100 Kelvin, pretty much zero particles are traveling at those kind of speeds. At 300 Kelvin, you can see that there is a small portion of them over here that are traveling at that speed. However, at 700 Kelvin, you can see that you have a much, much larger proportion of particles that are traveling at that speed. So what that tells you is that temperature is involved in the effectiveness of collisions, because the higher the temperature, the greater the average or mean molecular speeds, and as a consequence, the greater the kinetic energy of the particles. So let's look at now the rate of chemical reactions, and what we'll do is we'll standardize everything to the same concentration so that we can focus only on the rate constant. As you can see in this graph, the rate constant increases with temperature. Notice that the relationship, it's not linear, it's curved. And we can describe it by this equation here that is called the Arrhenius equation. Okay, remember K is the rate constant. Let's see what these other things are. E sub A is the activation energy. R is the gas constant. And T is the temperature in Kelvin. Notice that we are using the thermodynamic version of the gas constant, 8.314 joules per Kelvin per mole. So as a consequence, we want to use temperature in Kelvin, the absolute temperature, and we want to put in the activation energy in joules per mole. That way, all of the units will cancel out in that exponent and allow us to get a calculation that's free of concerns about units. The value A here is the frequency factor. We will address that later on. Now, this component here, we call it the exponential factor. Notice that it is a power of the natural base of natural logarithms, right? The E. And as I mentioned earlier in the lectures, anytime you have these kinds of functions, you're trying to describe things like distribution or growth projections or stuff like that. Now let's look at it purely mathematically. How does the exponential factor relate to the rate constant? All right, so let's consider this. Let's consider a reaction that has a high activation energy value. Look at the exponent. What does that do to that exponent? A bigger E means that the exponent is more negative. But being more negative as an exponent means that E to the minus whatever that number is going to be smaller. So that means that when you calculate this, not including A in this treatment, that makes K smaller, which means you're going to result in a slower reaction rate. Okay? Now let's consider temperature. Let's consider a high temperature value. Notice that the temperature is in the denominator of that exponent, which means that if you increase T, that makes the exponent smaller. The ratio of E to RT becomes smaller, and because we're taking the negative of that, that means that it's going to be less negative. Therefore, E to the minus that ratio is going to result in a value of K that is larger, and as a consequence, this is going to result in a faster rate. Okay, if you need to pause the video here to think about this a little more, feel free to do that. I'm not doing anything, kind of like ultra complicated. This is just pure algebra. Okay, so let's consider this exponential factor then and say that in general, what it's going to represent is the fraction of reactant molecules with sufficient energy to make it over the activation energy barrier. That's what the exponential factor is all about. Now, another thing we can do with this type of graph and this Arrhenius equation is notice that if we take the natural logarithm on both sides of that equation and we apply the rules of natural logarithms, we can arrive at an alternate format. And this is log of K equals minus E over R times the reciprocal of temperature plus the log of A. In other words, we have here the format of a straight line. That's correct. Y equals mx plus b, where m is the slope. So let's say you do a series of experiments and you find out what is the rate constant at different temperatures. And then you run a graph of the natural logarithm of K versus 1 over T. This is called an Arrhenius block. Notice that in this case, the slope of that line is going to be minus EA over R. Now, since the graph is giving you the slope and R is a constant, that means that you can use this type of graph to find out what is the value of the activation energy. And this is typically the way that we do this, to find the activation energy. Now, I would like to walk us through a couple of derivations to help us out with this, and then do a couple of practice exercises. Okay, so we'll be right back.
What we're going to do here is we're going to derive a two-point relationship between the rate constant and temperature. For those cases where we don't have a full complement of data of several rate constants at several temperatures, let's say we only have 2 data points. Consider the first one. The rate constant at temperature 1 is written here in the alternate form of the Arrhenius equation, right? So let's consider a value of K at a different temperature. So that would be, let's say, log of K2 equals minus activation energy over R. The activation energy, we assume it's going to be the same, 1 over T2 plus log of A, which should also be the same, since this is a factor we'll discuss a little bit later that has to do with the orientation of the molecules, not their energies. So let's do some algebra here. Let's subtract these two equations and let's see what we get. So in its basic form, we have log of K1 minus log of K2 equals, now when we subtract these two items here, we can factor out the EA over R. So I'm going to put those aside. EA over R. And then inside we're going to have minus 1 over T1 minus, right, negative 1 over T2. And what happens to the rest of it? Well, log of A minus log of A essentially cancels out when you subtract. Let's do a couple of things here now. Remember that when you have the logarithm of one value minus the natural logarithm of the other one, that is the same as taking the logarithm of the ratio of both of them. So I'm going to rewrite this as log of K1 over K2. And then over here, we're going to have the activation energy over R. Notice what we did here, we moved the negative signs with the temperature units. We left out just the activation energy over R. And so what happens here is, since this is minus minus, it becomes positive. And so we can rewrite this as 1 over T2 minus 1 over T1. And this is what is called, we're going to call this the two-point version of the Arrhenius equation. And this will help us in several This is going to help us in problems where we're only given 2 data points. All right. So let's go ahead and look at that.
We have derived the following expression. We call this, like I said, the two-point form of the Arrhenius equation. It turns out that sometimes when you have just 1 over T2 and 1 over T1, it's a little bit hard to carry out those operations in your calculator. And so many times what we do is we rearrange this expression. This is just algebra. We rearrange it into this form, which is actually perhaps more convenient. Okay, so take some time if you need to pause and add this equation to your growing list of equations there. And let's go ahead and do a practice exercise here. This may or may not have made it into your set of PowerPoint notes, so feel free to pause and copy it down. I'm going to walk us through the solution of this problem. So the reaction, CH3Cl plus water, giving CH3OH, which by the way is called methanol, plus HCl, of course, hydrochloric acid, has a rate constant of 3.32 times 10 to the negative 10 per second at 25 degrees Celsius. And the activation energy is 116 kilojoules per mole. What is the value of the rate constant at 40 degrees Celsius? Let's go to my camera and solve that problem by hand. Okay, thank you. We have derived the following expression. We call this, like I said, the two-point form of the Arrhenius equation. It turns out that sometimes when you have just 1 over T2 and 1 over T1, it's a little bit hard to carry out those operations in your calculator. And so many times what we do is we rearrange this expression. This is just algebra. We rearrange it into this form, which is actually perhaps more convenient. Okay, so take some time if you need to pause and add this equation to your growing list of equations there. And let's go ahead and do a practice exercise here. This may or may not have made it into your set of PowerPoint notes, so feel free to pause and copy it down. I'm going to walk us through the solution of this problem. So the reaction, CH3Cl plus water, giving CH3OH, which by the way is called methanol, plus HCl, of course, hydrochloric acid, has a rate constant of 3.32 times 10 to the negative 10 per second at 25 degrees Celsius. And the activation energy is 116 kilojoules per mole. What is the value of the rate constant at 40 degrees Celsius? Let's go to my camera and solve that problem by hand. Okay, thank you.
This exercise is going to let us practice with the two-point version of the Arrhenius equation. So let's write that out. The way we derived it, or hopefully you were able to work this out also, is log over K2 over K1 equals activation energy over R, and then we have T2 minus T1 over T2 times T1. So this is the, we call this the two-point form of the Arrhenius equation. Now there are, just like in any other algebra problem, there are certain values that are given and one typically that we have to calculate. So what is given? Well, the first thing that's given is the value of K1. And this is 3.32 times 10 to the negative 10 per second. All right. And this is at T1, which we're going to call 25 degrees. However, in these types of problems, we need to convert to the absolute temperature scale, remember? So to convert to Kelvin, we add 273.15. And because the number given doesn't have any decimals, the result here cannot have any decimals, so we'll round it to 298 Kelvin. Now, our second value here, our second rate constant, well, that's our unknown. And this is going to be at a temperature T2, which is 40 degrees. But again, we have to convert that to Kelvin. And since, once more, there are no decimals, this has to be rounded to a no decimals version of the absolute temperature. So if we look at the equation here, we have the two temperatures. We have the K1, the first rate constant. We need to calculate for K2. What else do we need? Oh, we need the value of R, and we need the value of the activation energy. So R, according to our Google or data table sources, is going to be 8.314. Careful with the units, joules per mole Kelvin. And the activation energy we're being given here is 116 kilojoules per mole. But since we're going to have to cancel out units with the R constant, we need to convert that to joules. So this is going to be, there's 1,000 joules in 1 kilojoule. Or alternative, you can simply essentially roll the decimal period 3 spaces to the right, correct? So let's put in the values in our equation here. So we have, we have log of K2 over K1, which is 3.32 times 10 to the negative 10 inverse seconds. Now, K2 will also have the same units, which means that those are going to cancel out. We'll do that in a moment. Now we have the activation energy over R. If we calculate this here, we have 116,000 joules per mole. And we have R, which is 8.314 joules per mole Kelvin. And now we have the temperatures. Big parenthesis here, huh? So T2 minus T1, so that's 313 minus 298 Kelvin. And in the bottom, we're going to multiply them. So that'll be 313 times 298, and that'll be Kelvin times Kelvin, so that'll be Kelvin square. Okay, at this point, before we put numbers in the calculator, let's make sure that we've set this up correctly. Since this is a natural logarithm, all of the units should cancel out. So we see that inside the natural logarithm, the inverse seconds are canceling out, so that's good. Here we have joules per mole with joules per mole. Those cancel out. Now we have this Kelvin here, which can cancel out with one of these. And then since this Kelvin unit was in the denominator or the denominator, it flips up and therefore can cancel with the other Kelvin unit that's in here. And so we don't have to worry about, excuse me, about any issues with this kind of stuff. All right. How you do this in your calculator? Well, it depends on your calculator. So my calculator is very simple. It doesn't have a lot of functions in it. For example, I cannot put parentheses and kind of like do cumulative calculations. I had to do them kind of in a row here. So what I'm going to do here is I'm going to start with the 313 minus 298. And that should be the same as 40 minus 25, in other words, 15. And then I'm going to divide by this. Now that's the same as dividing by them twice. So divide by 313 by 298. And that gives me this number in there. I'm not going to round anything yet. So now I'm going to multiply that times what's in here. So times 116,000 divided by 8.314. And that equals that. All right. So let's say this is going to be a number that I'm going to have to be rounding, but essentially it'll be rounded to 3 significant figures in the end. Actually, this will be only 2, so technically it's going to be 2, but I'm going to keep it at 3 because that's what I'm going to get over here. So let's say this is 2.24. And that means, therefore, that if I take the base e and I elevate it to each one of these exponents, so e to the log of something is whatever is inside it, because that's the definition of the natural logarithm, right? So this is going to be K2 over 3.32 times 10 to the minus 10. All right. And that'll be equal to e to the 2.24. And now my last step is to solve for the value of K2. So I'm going to clear this guy out, and I'm going to say K2 equals 3.32 times 10 to the minus 10 times e to the 2.24. Now, I'm writing this in here, but actually I left that product that I have from all this operation here in here. So what I'm going to do right now is, again, in my calculator, what you do is I have a shift here and then e to the x, so it'll elevate e to that power, and I'm going to multiply times 3.32 to the 10th power, and the result is 3.13 times 10 to the minus 9 inverse seconds. Now, before I upload my answer to a quiz or test or whatever, let's consider this. Does that make sense? Is that a reasonable result? Remember, what we know is that the value of the rate constant should increase with temperature. So if it had a value of 3.32 times 10 to the negative 10 at 25 degrees, we would expect that at 40 degrees, that number should be larger, should be bigger. And it is. Okay, maybe we made a kind of like a math error or something like that in our calculator. That happens. But remember, in all kinds of testing situations, I'm always asking you to show your work. And that way, you can tell if you did it right or not. But you should always check, does the final answer make sense? Is it in the realm of what I expected? If it had come out lower than the value of K1, something is wrong. Now, maybe you made a mistake here or there. You put, 8.134 instead of 314. Things like that happen. But, it may be that the number you get here is slightly different. That's okay. I can tell if I see what you did, where the mistake was, and I will give you, at the very least, partial credit for your answer. Okay? So let's go ahead and go back to finish our lecture.
Let us consider now the importance of the molecular orientation. Remember Arrhenius' equation. Remember that the equation includes a term, A, which we call the frequency factor. There are two components to A. The first one is called the collision frequency. This is the number of collisions that happen per second. The second one is called the orientation factor, P. This is a statistical term representing the fraction of collisions that have the proper orientation. And the way we represent A is simply by the product of the orientation factor times the collision frequency. If you want to read more about this, your textbooks have plenty of explanation about this, and they go deep into it. We're not going to go that deep. I'd rather use more of a visual representation of the importance of molecular orientation. So let's go ahead and look at this reaction here. This is the reaction between carbon monoxide and nitrogen dioxide gases to produce carbon dioxide and nitrogen monoxide. Now, what happens if we look at the three-dimensional models of these molecules, we can see a little better of what's happening. For example, here is the carbon monoxide and the NO2. Remember, the goal is for the NO2 to transfer one of the oxygens, that would be one of the red spheres, to the carbon in the carbon monoxide to convert it into carbon dioxide, CO2. So notice that if they collide in this orientation that I'm showing here, that is feasible to make that transfer. In other words, the carbon will collide with one of the oxygen atoms on the NO2, and that will facilitate the formation of the carbon dioxide, CO2. Notice that the NO2 loses an oxygen and it becomes NO, nitrogen monoxide. Now, what happens if instead of this effective collision, we have the following? Notice that in this case, the carbon of the CO is colliding with the nitrogen of the NO2. That is not what we're looking for. And so what's going to happen is they're just going to bounce off of each other because that is not an effective collision. This is an ineffective collision. So in other words, realize that in order for chemical reactions to happen at a considerable rate, they need to collide. The molecules need to collide not only with sufficient energy to overcome the activation energy barrier, but they also have to collide in the right orientations so that you will have a chance to make the necessary chemical bonds. And these two components, the energy component and the orientation component, both play a major role in the rate of chemical reactions. Now let's consider some of the factors affecting the reaction rate. What I'm going to do is I'm going to talk about some observations that we can make that are repeatable, and then let's see how we would explain those observations using the collision theory model. For example, concentration. It is known that the larger the concentration of reactant molecules, the faster the reaction. The idea is that the larger the concentration, this increases the frequency of collisions. Let's look at this diagram here. Look on the left, there are only two red spheres trying to collide with the blue ones. Notice that it's not going to be as effective because the ratio of concentration is not enough. However, on the right side, where you have a higher concentration of reactants, you have more of a chance of them colliding. I have a trivial example for this. Imagine that we put 5 students in a classroom and we blindfold them and ask them to move around, at a very slow pace. And we've removed all the chairs from the room and we measure, how many times they collide. Well, they're going to collide every now and then, but it's not going to be as frequent as if instead of 5, we put 50 students in the same classroom and we blindfold them and ask them to move around. Obviously, the more crowded the room, the more frequency of collisions we're going to have. Another observation we can make is the nature of the reactants affects the rate. For example, it is known that small molecules tend to react faster than larger molecules. Gases tend to react faster than liquids, which in turn react faster than solids. Remember from your Chem 1A class, the degrees of freedom of motion of gases is very high. In other words, they can translate themselves, they can vibrate, they can all that stuff. But in liquids, the amount of movement is more limited, and of course in solids it's almost null. So gases have greater kinetic energy, and therefore they will have a greater frequency of collisions. In the same way, small molecules tend to react faster because in small molecules the orientation factor is not going to be as important as it is in large molecules where the proper orientation is going to be key. Another thing we've observed is that the physical condition of reactants also affects the reaction rate. For example, powdered solids are more reactive than blocks or cube crystals. And that's because you are offering more surface area for contact with the other reactants. In other words, for collisions to happen. So here we have, follow this animation please. Notice that only the outside atoms can react, but if we kind of like stir it up and break them up, now you have less atoms ready to react. Okay, let me show it to you again. Let's split up the crystals into smaller ones, and notice that when we split it up into smaller ones, now every single atom is available to react with the blue reactant. Okay, so more surface area also explains why in the example that I gave you in the beginning, we said that if we apply heat or a flame to a steel nail, we might get it to bend a little bit, maybe even melt if the flame is hot enough, but it's not going to combust. However, if we use a steel wool, where the atoms of iron are more exposed to the oxygen, you can have a faster reaction, which then produces an effective combustion. In the same way, reactions generally occur faster in solution than with pure substances. For example, if I put two solids next to each other, the amount of reaction is going to be minimal because most of the solid atoms or molecules are not even in contact with each other. However, once you dissolve them, mixing gives more opportunity for particle contact. Another observation we make is that temperature seriously affects the rate of reactions. Generally, and I emphasize generally, increasing the temperature increases the reaction rate. There are exceptions because sometimes increasing the temperature actually causes some of the reactants to become unstable. Actually, there's a little rule of thumb that chemists have that for each 10-degree rise in temperature, 10 degrees Celsius, the speed of the reaction doubles. Why is this? Well, remember, higher temperature means that the molecules have a higher average kinetic energy. And therefore, you're going to have a higher frequency. I mean, the molecules are moving about faster. So you'll have a higher frequency of collisions. And you'll have greater energy of collisions. Here's an example. You can see the example on the left. At low temperature, particles A and B have very small range of motion. So it's not as likely that they will collide with each other. In the example on the right, at high temperature, you can see where the ranges of motions of particles A and B are broader, and so there's more chance of collisions. Another kind of trivial example that I use is, imagine that you take a parking lot and you put 10 cars in there, and you have them essentially move about. Again, the driver is blindfolded at 5 miles per hour. You expect that there'll be a collision here and there. But what if instead of driving at 5, you put them to drive at 30 miles per hour? Yeah, it is more likely that they're going to collide more often and actually perhaps more seriously, right? Okay, so the last factor that affects reaction rate we'll consider here is catalysts. So a catalyst is a substance that affects the speed of a reaction without being itself consumed. Most catalysts are usually used to speed up a reaction. In other words, a catalyst typically does not slow down a reaction. Usually it speeds it up. Now, we're going to save this topic for our last section when we talk about mechanisms of reactions. All right? So those are the factors. So what I want you to do is go back, think through these things in the context of collision theory, and try to think of how these different factors we've discussed are going to be able to affect the rate of chemical reactions. Okay, that concludes the third set of lectures in studying the topic of chemical kinetics. Please take time to go back and review everything we discussed about activation energy, the Arrhenius equation, collision theory, and the factors that affect reaction rates. Now we are ready to tackle the next topic, which will be reaction mechanisms. How do we think that a chemical reaction might happen? How can we break it down into small elementary steps? We'll see you soon. Thank you.